Question 2 is a question about halogenoalkanes, and the first thing we have to say is suggest how the methoxide ion, that's the CH3O- ion, suggest how that acts as a nucleophile. Well, we just need to give the definition. So it's going to donate a pair of electrons, and that's going to come from the O- lone pair. We need to suggest a mechanism for the reaction. So if we just remember, we know about the hydroxide ion mechanism. So if you can see the similarity there, instead of OH minus, we've got OCH3 minus. Exactly the same mechanism. So curly arrow from the lone pair on the O minus to the carbon with the slight positive charge, and that's going to repel the electron pair in the CBr bond onto the bromine and break this bond by heterolytic fission. So we're going to make this product here, and we're going to get a Br minus ion because this bromine has effectively gained an electron. So if you think about the pair of electrons in that bond, one of them belonged to this bromine, the other one belonged to this carbon. We're then asked to compare the rate of hydrolysis, or the rate of reaction, if you used one iodobutane instead of one bromobutane, and the box that you would need to tick is the middle one here. Iodobutane would increase the rate, and that's because the Ci bond is weaker or has a lower bond enthalpy than the CBr bond, and so it's going to break more easily. And they're throwing another nucleophile at us. This is the ethanoate ion. We just apply the same logic as before and work out the structure of the new product, and we're going to get this ester now, and this is called butyl. So this is the butyl part, 1, 2, 3, 4 carbons, butyl, 1, 2, ethanoate. Bit of a calculation now. So we're given the MR of 1-bromobutane, and it can be made from a reaction of butan 1-ol shown in the equation below. Calculate the atom economy. So atom economy is the MR of the desired product divided by the MR of all the products multiplied by 100. So there's our desired product. So it's the MR of that divided by the total MR times 100. So we get 47.03%. Bit of a nasty addition here. Suggest a reactant other than a different acid that could be used to improve the atom economy of making 1-bromobutane by the same method. So we're not allowed to change this. So we've got to change this here. So it's got to be something that's going to that's going to increase this number. So we need something with a lower MR. So it still needs to be something Br. So we're going to go for, I've gone for either lithium bromide or sodium bromide. So if you think about it, what that's going to do is when you divide by the mass of all the products, you're going to be dividing by a smaller number if you use lithium bromide or sodium bromide as opposed to potassium bromide, and that will effectively give you a higher percentage answer. And then the final part, a student prepares a sample of 1-bromobutane. So we're told 5.92 grams of butan 1-ol is reacted with an excess of sulfuric acid and potassium bromide. After purification, we get 9.72 grams of product. Calculate the percentage yield. So we've got mass of butan 1-ol, so we can work out the moles of that. So there's the calculation there, 0.08 moles of butan 1-ol formed. The 1-to-1 ratio in the equation means that we should get the same number of moles of product. And then what we need to do is calculate, well, actually how many moles of product were made. So that's the mass produced divided by the MR of the product. and so we get 0.071, and then we need to express that as a percentage. So remember, it's actual over theoretical times 100. And the calculator value is something like that, 88.7509, and more and more numbers. And we have to give our answer to 3 significant figures. So there's our third number there. Check the fourth one, that's a 5. So this goes up to an 8. So it's 88.8.